Good morning, everyone. So welcome to lecture 6. Today we will learn what is deep learning. And today we will solve a fundamental problem to understand how a neuron works. So guys, first of all, let us know what is deep learning. Deep learning is a type of machine learning where neural networks learn very complex patterns in data. So guys, when a machine can learn very complex patterns in data, that is known as deep learning. And the word deep came from that we use many layers, or the neural net can be very deep. So on your screen, you see here, we have an input layer. And inside the input layer, after the input layer, we have a deep neural network. And this deep neural network has right now 1, 2, and 3 layers with it. And like this, it can also have n layer. What does one layer made up of? One layer is made up of multiple neurons here. Here 1, 2, 3, 4, 5. So this is one layer which consists right now on your screen 5 neurons. And the second layer also has 5 neurons. And the third layer also have 5 neurons. So this can be a very deep neural network. That means it can have n layers into it, depending upon the context, the problem, the complexity of the problem. You can decide how many layers you want to choose. And finally, you have output layer where we get our final probabilities out, or our final answers out. So overall, deep learning is very deep because it consists of many layers which can learn very complex patterns in data. Definitely, deep learning is inspired by human brain. So deep learning exactly mimics how our brain learns pattern. For example, in our brain, we have neurons which process information through layers, and each neuron is also connected among themselves with something that we call as synapse. It is connected, these connections, that provide the information from one spot to another spot. And finally, we have neurons, connections, and the layers similar to human brain. Now, neurons also learn from example. For example, the brain, it recognizes a pattern. How does the brain recognize the pattern? It sees a dog. A dog has fur. It has 4 legs. And we see it again and again. And we know that, okay, anything that we see with, 4 legs, fur, and looks like dog, maybe the height or maybe the special features, we know that, it's a pattern of a dog. And it is the same way that a neural network learns. Then it's the same thing as our brain. It goes from input to output. Neural networks also do the same thing. There is an input which is of image, text, or sound, and it produces results, which is called, you call it a dog. And deep learning is also very powerful. And if you can scale it, you can learn complex relationships, which will improve with more data. Of course, you need to have a deeper neural network, larger amount of data to understand and to mimic something, like a human brain, or mimic very complex patterns in data. So guys, so on your screen here, we have a neural net. This is how a neural net looks like. Input layer, hidden layer, output layer. Hidden layer can be of multiple neurons. As we saw, this is layer 2. And input layer is where, we give, our inputs such as image or text. This input layer, it converts. The idea is that this input layer, we give the input as numbers. So if we go and look at the computer vision lectures, we will see how a image is converted into numbers. Similarly, we know that a text is converted into embedding, and this is also a number, and everything is given as an input layer, and then we have this hidden layer which definitely form of neurons, and and are connected, and finally we have an output layer where we have the answers to our problems that we are doing. If we are classifying an image, we know that it's a dog, bird, or a cat, or if we are classifying an email, we know that it's a ham or a spam. It's the same concept, just that words are converted into word embedding and images are converted into numbers. And this entire bootcamp is about LLM, but you can go on my on the YouTube channel, and you will find some lectures on computer vision, and there you can learn that how the image is also converted to numbers. Okay. So guys, today we will learn very fundamental concept. So the concept is what is happening inside the neuron. So guys, this is a neuron that you see. So from those stack of neurons and from those layers of neuron, now I am just going inside one neuron. Now, what is happening inside one neuron? So guys, see here, the neuron is connected to, your input. So your input here could be your embedding. This could be your embedding. And this could be your input. And now this embedding now is going inside the neuron. And this embedding is going inside the neuron, and you can say inside the neuron, this is the mathematical operation happening. That means your output, that is your y, is somehow related to your input, your x1, your x2, and your x3. And let us take an example to understand how your output is related to x1, x2, and x3. So guys, we are doing a dementia prediction neural network model where we have three input features. We have an input feature called age, another input feature we have diet, another input feature we have exercise. So like it would be much better to understand by this example, because embedding embedding consists of a lot of numbers, and it is very difficult to present that kind of model for learning purpose. So what I'm doing is I have taken an analogy of the same problem, where instead of each word, which will be one input variable, I have here some input features. I have age, I have diet, I have exercise. Together, they are going inside the neural network, and I have a probability of dementia coming out. So let us learn now how this model is working. So guys, on your screen, what you see here is I have a data from the hospital. And what is this data? I have age of the people, and on the y-axis, I have here, whether the person will have dementia or not. It is, the person, if he has a dementia, it is by 1. If the person doesn't have dementia, it is by 0. So on screen, you have age versus dementia. Now, what is happening when you have this column of age? So you see here, the person who are younger, they have no dementia. The person who are older, they have dementia somehow. So guys, here 1 or 2 numbers will be outliers, but the general trend, if you see here on the screen, I have plotted. This is your y here, this is your x here. And I have plotted y versus x And what do I see here? Y versus X. I see that there is a relationship between them, between Y and X. What is that relationship? That relationship is, Y has certain kind of dependency on X. And mathematically, sorry, this is X. And mathematically, we can, fit this dependency that Y is proportional to X by the equation of line, which is Y is equals to mx plus c. So how much Y depend on X is given by the slope m, which is also the weight that you actually train in your neural network. So this is the famous equation that we have in the neural net. Y is equals to wx plus b. And for your parameter, for your variable here, which is your age, so y1, because this is your first variable, it is, the answer is coming out to be 0.23x1 minus 0.57. How do I approach this answer? I did nothing. I just went in Excel and try to fit it, and I got this answer, that where my m, so m, so in the equation of line, which is like this, y is equals to mx plus c, where m is your slope and c is your intercept. This is your c. So here, so c is 0 because it is not forming intercept, but my slope would also be like this, and then this will be my intercept. Why my slope will differ, guys? So on your screen, you see here, I have y and x, and a person can fit a line that is like this on the screen, but another person can fit the line like this. Third person comes and he says, no, this is the best line. So the idea is that this is C, which is your bias. It is also a slope. Sorry, C, it is your bias. It is also your intercept. So the idea is you can fit it by any line, but the idea is we want to give this kind of flexibility in the mathematical equation, because what we are trying to do is, guys, we are somehow trying to have LHS is equals to RHS, which is a very, delicate procedure, because here we are somehow looking that your Y should exactly be, exactly be multiplied with its weight. However, this is not happening. We have to give it little flexibility, it's always not possible here, that your Y is, it is a multiple of X. So to do that, we have this little flexibility, which is your bias, and which is also your intercept in the line equation. Now, this is what, okay. So overall, guys, this is what we understand, that age here has a relationship with Y, and this relationship is given by M, which is slope in the equation of line, which is here 0.23, and this slope, which is 0.23, is famously known as weight, because this much weight age has on final dementia, right? That this much dementia depends on the age. And this is your B, which is your bias, which is minus 0.57. And this is the intercept here. So in this equation, this will be it. Similarly, I have for you all the other features also plotted. Now, dementia, guys, as I told you, it not only depends on your age, it also depends on exercise per month. So on your screen here, you have the data where you have exercise days per month. And you see here that person who does the exercise, here more 14, this is outlier again, 7, 18, 14, 17, 12, that all the person where they are exercising, up to 14 days per month, that means they are exercising alternative days per month, they have zero probability of dementia. They all have zero probability of dementia, right? Whereas other people, that means if you look here, the people who are exercising, they have zero probability of dementia. Whereas the people who are not exercising, they have very high probability of dementia, which is 1. Now we do the same thing. We have a mathematical, question here where we have y and x, and again we try to fit it with the equation of line, and we get these two as our main variable. This is your w and this is your b. So here your bias is 0.81, and you see here, guys, mathematically you can also see that we are close to 0.8. So the intercept is 0.81. Now this is your bias and your slope is 0.53. And this equation can change, if somebody comes and say, no, I think this is a better fit, then this will change, right? And so this will become your bias. So that is why this is the kind of flexibility we have. And that is why we call it, we need the best weight or we need the best fit. So this is the idea behind it. So like this, we now know from this equation that the parameter 2 that we have here is also, finally contributing to, the final output of dementia. So this is where, you can do this for every parameter we have. So guys, third parameter here on the screen is junk food per month. Now, what is junk food per month? So guys, on your x-axis, you have here, junk food per month. You have, when you have less, more healthy food you eat, or, you eat less junk food, you just eat few diets of junk food, you have no dementia. No, you have no dementia. Wherever if you are having a lot of junk food, you will have dementia. Somehow the quality of diet is contributing to dementia, and we want to find this relationship. Now to find this relationship, we do again the same thing. We plot junk food on x, we plot dementia on y. We want to take a relationship between x and y. To do that relationship, we fit an equation of line, and the equation of line here we know is y is equals to mx plus c. This is the equation of line, and we fit it here, and when you fit it, you have m here as a slope. That means this much is the relationship, or x when multiplied to this much of slope, it contributes to my y, right? So this is the relationship between them, and here we have a very, very little bias because our line is passing through 0, which is 0.04. So we have again, done the third parameter here. Now collectively we will see what happens inside the neuron. So guys, now what happens is, here on screen you have 3 independent variables: age, exercise, and diet, and somehow they have a relationship with the dementia, and this relationship is quantified by 0.23, or you can say it is a weight. It is a weight that age is dependent, age parameter has this much weight that would finally contribute to dementia. And here also, this is the weight 0.53 that is multiplied to x, and this will contribute to dementia. And similarly, we will have this diet that will contribute to dementia. Now together inside the neurons, if you remember, this was my neuron, and I have these 3 parameters, y1, x1, x2, x3, and there was a y, which actually, if you go inside it, it is made up of y1 plus y2 plus y3. This is your final output inside the neuron. So neuron, what it is doing is it is taking output from all the inputs and adding it up, right? So now this here, guys, so this is what is the fundamental behind it. Any problem, why deep learning became so famous, because any problem can be divided into these three parameters. Any problem, meaning that you have the problem, whether it will rain tomorrow. You can divide it into multiple factors. You can divide it whether the first month, whether it's a month of August, probability is high it would rain. Whether the location is in tropical region, it would rain. Whether there is some kind of special forecast or hurricane around, it would rain. So this is one problem, that it would rain, it divided into all these three factors. Like this, any problem you can imagine, you can divide it into the problem would be dependent upon certain factors, and that certain factors will have a particular weightage on that thing. So this could be any problem. For example, what is the price of this house? The price of this house will depend upon all the factors that we have: location, the plot size, the bedroom, whether the construction is new or old. And this, maybe out of this four factors, that is the land area, number of bedrooms, location, and the build or not, one of them will have very high weightage on the final answer, right? And idea is to determine that weightage, and that weightage is given to you here by this slope here, because it is simply every problem is divided into this, that your final problem depends on your multiplication. There is some kind of multiplication, or there's some kind of linear dependency on the x. It is linearly dependent on x. So this is what is happening. And finally, y is equals to y1 plus y2 plus y3 is what is happening inside the neuron. So guys, I hope this was clear. Now, the main other important concept that we have to learn is that, guys, inside the neuron, so you can have here, if this is your neuron here, and this x1, x2, x3 are your inputs that are going to the neuron. This is final y. So you will have an issue here. The issue would be because we haven't really normalized anything here. Here age has its own unit, dementia has its own unit, diet has its own unit. So we will have different mathematical numbers that we want to add. So these mathematical number, maybe one where it will be like this in at a decimal place, at a fourth decimal place. Maybe somewhere the weightage is like this, somewhere even weightage is like this in some numbers. What the idea is to bring all these numbers on one scale. And to bring all these numbers on one scale, we use something called activation function. So this is inside the neuron, and we have here output, and this output y1 plus y2 plus y3, it goes inside a function. Here we have a sigmoid function in front of you. So activation functions, when you start building your projects, could be multiple. One could be sigmoid, other could be your ReLU, and I will introduce this thing tomorrow, that we want to scale the output, all the outputs between 0 and 1. Because once we scale it between 0 and 1, then it becomes very easy for us to take a decision. So here you see, I will put my y1 here and I will have a number. Then this number will be somewhere on this plot. Then I will have, y2, that will have a number, and this will be somewhere on the plot. Or you can say, basically, it is the addition of y1 plus y2 plus y3 that is on your plot right now. Because imagining it individually would be much more complex. So this is your final, your neuron. You have a, in the neuron, you have your output. You want to scale that output in, between 0 and 1. And that is why you apply the this activation function, which is sigmoid, which looks like this. And finally, your output from the neural net also becomes like this. Okay. So guys, overall, this is how inside the neuron it works. This is one neuron, guys. This is neuron 1, where this neuron 1 has a relationship with all input parameters. Similarly, there will be neuron 2. Do not forget that. It will also have relationship with all these ones. Similarly, we will also have neuron 3. So all this neuron 1, neuron 2, and neuron 3 will have, some kind of addition of all the final, y1, y2, y3 that will be there. So for example, if you have neuron 1, you have here, y is equals to y1 plus y2 plus y3. There will also be neuron 2, which will also have, y1, y2, y3, but maybe the fits were not the same. In the beginning, our fits were like this. Maybe in y1, y2, y3, this is how our model learned. The numbers would be slightly different, because finally, in the neural network, we are taking the average of neuron 1, neuron 2, and neuron 3, such as, till neuron n, and that average is finally contributing to our final answer. This is very complex. That's why I was trying to break the problem from one neuron. And, inside one neuron, this is happening. Then the same thing is going inside another neuron. Then the same thing is going inside the third neuron. And like that, it is going inside the n neurons. And finally, our output y is the average. So guys, this will also go, all these 3 neurons can also go to another neuron. So if you remember, this is, from previous drawings, that you had multiple neuron layers. This was the neuron layers. And each neuron is connected. So this is very important, like this. This is your answer by neuron 1. This is answer by neuron 1. This is answer by this all. First neuron, second neuron, third neuron, fourth neuron will go to neuron 2. First neuron, second neuron, third neuron, fourth neuron will go to neuron 3. First neuron, second neuron, third neuron, fourth neuron will go to neuron 4. And like this, we will have the average of each neuron. And then you can have another layer if the pattern is more complex. That is why it's a neural network. It's a very big neural network. You can choose, this from 16 to 32 to, 64, 1024. You can choose any number you want. Generally, people go up to even higher numbers and build, a neuron layer of 1024. That means the final answer is the voting by 1024 neurons. Okay, I hope this was clear. And if this was not clear, guys, it was you watch the video again, try to understand what is happening inside the one neuron, and then try to replicate this procedure, that every neuron will have the same inputs, but the answer will slightly vary. Here we are looking for a precision, so we are adding up and being very precise and adding up all these inputs. So guys, here on screen, this is what is happening. Now your model is ready and you have different data sets. Now there's a patient that comes here and he comes to you and he says here that, I have age 21, I exercise a lot, I don't, eat zero junk food. What is the probability that I will have dementia? So, this is the equation that you plug in and you finally get an Y. So guys, one important thing that we had, you remember, we had a sigmoid curve. Finally, all your Y outputs were converted into the sigmoid here. And this Y outputs were converted into the sigmoid. So this gave us a very good opportunity that, we can simply say that at 0.5, we can decide a threshold here. That at 0.5, I want that, the finally Y, so this is your Y, that above 0.5, I want that, all the numbers that comes, that I will have a probability of dementia. And below 0.5, I will have no probability of dementia. 0. So this is 0, this is 1. So if my final Y output is 0.59, I will have the probability of dementia. If my output is less than 0.5, I will have no probability of dementia. Does it make sense? It's a slightly complex topic, which you should be able to understand now. I hope this was clear, guys. Okay. Now I developed this code for, for actually, now if you see at this code here was where, we had the data from the university, sorry, from the hospital, where we are able to, in this data, have this plot, and we have something. So guys, you have a straight line here. So what we are fitting is y is equals to mx plus c, right? Same thing here. We have the data. We are doing y is equals to mx plus c. So we have the value of m. We have the value of c. Now, in the third one, we have here junk food, dementia. We have here mx plus c. And, you can take this sheet and play. Now, finally, I have here y is equals to mx plus c, and I have just added this thing here. Now, what has happened here after adding? So there is a parameter here. So there is a data case I'm taking. Age of a person is 16. Exercise is 30. Junk food is 28. Whether he will have dementia? He says yes, because it is just coming by y is equals to mx plus c. And I have applied here the sigmoid function. And now if I make the age is equals to, say, 76, numbers are changing, and he says that, he will have dementia. Now let us take the number age as 2. His age is very young. Exercise is, he does exercise, say, 17 days. He doesn't eat the junk food. He takes 2. Whether he will have a dementia, no. And this simple classifier that I built, I just built it using the technique that I told you. And this is the most easiest example that we have. That means each of these age, exercise, and junk, here, it will finally contribute to my classifier, which is yes or no, right? That is what I have built here. Okay, I hope this concept is clear. It is the number one concept to be, understanding. Okay. Now, with this thing, we are doing one, you know, so guys, concept of activation functions, neurons, this thing will become more clear in one or two more classes, which are building on the same problem. I will tell you about the famous thing about learning rates, loss functions that you will come across the code today. Now, on your screen here, we are today doing spam classifier using neurons. Now, how are we doing spam classifier using neuron? Now, on your screen here, you have the word embedding vectors. So it is the same problem, guys. You will go here. You will go here the same problem. You will give your text here. The text would be converted into this embedding. And you can use any of the techniques that I told you of the embedding. You can use glove, you can do engram. And after that converts into embedding, it goes into the input layer. And now you can convert this into ham and spam. Now, what is the analogy that you're thinking to the dementia case that we have? Now here, you will have, a big text, a text like this you will have, where you have a text like this. Win a free iPhone, it's a spam. Congratulations, you won a prize, it's a spam. Meeting at 5 p.m. today, it's a ham. So what is happening here is all these things are converted into an embedding. And here, there will be, because there are only two labels here, spam and ham. So there will be similar thing as we told to you between 0 and 1. 0 will be for maybe for spam and ham is 1. And each of this thing is corresponding to this label here. And so you will have your numbers here, multiple numbers here, which will be always pointing to 0 if it's a spam, right? Here, sorry, 0 means spam and 1 is ham. So all these numbers will always point to this thing. And this in between comes this neural net that you want to train, right? So here, this is what is happening here, that you have age, exercise, and diet, and you have this pattern that you told. Here we will have this text embedding, and there will be a weightage given, to these labels here. And that embedding is finally adding to this y, where you have, for example, let us say an example to help you clearly understand. Now, on the screen, how will you do a spam classifier? You have win a prize. Now, win a prize. Now, second will be, uh, hurry, sale is on, something like this. Then other is from your boss, or from me, meeting at 5. Now, these are three things. Now, this will be converted into an embedding. And that embedding that you have, it goes inside this and contributes to something called Y, which is either spam or ham. Basically, it's a number 0 or 1. So all these messages, win a prize, they will contribute somehow, and it will learn in a way that we will have weights here that will change. win a prize and sale, they will, give a weightage together so that it contributes to something called, y is equals to 0. And this is exactly what you're doing in your neural network. When you have a meeting at 5, you will contribute to something called 1, finally. And this is how your weights are playing. And how your weights are getting trained, your different functions that I will talk in next, lecture. But overall, today, you are doing this code activity with me, where you are classifying this win a prize, hurry, and meeting using neural nets. Let's do it. Okay. So guys, on screen, what you see here is, okay, let's see again. You are importing different libraries. Let's talk about the library now. So as I told you, you have words and you can convert those words using any of the embedding model, either glove, or you can use here, corpus from the glove. Yesterday we did corpus and glove, right? So one important is glove. Now you are introduced to very famous libraries, right? TensorFlow, Keras. So what does TensorFlow and Keras? They are basically the libraries, the most famous ones that are known to train neural nets. And here you have, model that you are importing sequential. Because why we are importing sequential model? Because we are going from one, neuron to another. We have everything in the sequence. So we have a model called sequential. Now we have layers here. We are importing layers here. We are importing layers, we are importing 3 layers: dense, embedding, and flatten, because our model is like this. We have embedding here. And embedding are basically, we flag them. So I will tell you that embeddings are in this matrix form. Then we flag them. Then we are putting it in neural nets. And finally, we have the output, right? So overall, then there is something called sklearn. Sklearn is all about train, test, split. It's a lot, depending on the model selection and pre-processing. And these are the 4 libraries that you are going to import. Again, you will import glove, that we know. NLTK, we know. We know from tokenizer, we have been talking about NLTK. Glove, yesterday we learned. 2 more libraries today I introduced to you. One is sklearn and TensorFlow. And this is to deal with neural nets. Neural net is a sequential model. That's why we are importing sequential. Here we are using dense, embedding, and flatten, because dense basically coming all from the embedding. These are different functions that we have inside this TensorFlow that we use for our convenience, right? Okay. After that, what happens? And I've been using the same text for you guys since, class 1, so that there is no confusion. We have the same data set. We know this data set very well. Wherever there is a win, congratulations, and you won, it's all spam. Other ones are all ham are good. And these are the labels. And what do we understand that? These labels would be converted inside as 0, 0, 1, 1, 0, 1, 0, 1, right? And these will be converted into big embeddings. And this is your X train. This is your Y train. Remember? X train, Y train. We remember it very well. And the idea is that we are trying to train neural net so that, we know that this X train is matching to, say, spam is 0. It is matching to 0. Ham is 1, it is matching to 1. Spam is 0, it is matching to 0. Ham is 1, it is matching to 1. This is what we are training. We are training our X train to our Y train. This is known as machine learning training, right? And then we are testing it. We are testing it because we divided the data into some part of the data we take from here and we test it, right? I hope this is clear here. Now, going at the bottom here, I am just tokenizing my messages. This is a code from yesterday. I am tokenizing the message called from glove. If you remember corpus get fit, I told you yesterday, we tokenize our text. After tokenizing it, we are fitting it to generate the embedding, and it is generating the embedding. So guys, this is, we are generating embedding, and here, so if you see here, this won't work because I need to import the libraries from the top. That's my bad here. Okay, let's do this. So you have to install Python. You installed it. And we are doing it together now in the teams so that everyone, is motivated. We have imported it. Another library is NLTK. I'm importing 4 libraries here. Okay. Now I'm starting tokenizing it. So guys, this tokenizer itself is based on, your neural net. So here glove. So remember if you remember from yesterday, your corpus and your glove, corpus.fit and glove.fit. Corpus.fit is basically, it just tells me how many words I have to take next. Glove.fit is actually depending on the number of dimensions I have. And here it is fitting everything here from 0 to 29. I'll just take 5 more minutes to end the class. And it is just training. And if I use the train here, because here I'm taking 50 dimensional embedding. It's a big embedding that I'm taking, right? And this I'm putting it here, and I can change this number if I take, 10 epochs. It will just do 10, right? So I'm still generating embedding, guys. After generating embedding, now I'm doing my actual work. What I'm doing my actual work is I am converting them sentences, right? And also splitting my data. Basically here, the main important thing is splitting your data that I have been talking about. This is extra that is coming, pre-processing of the embedding that we generated, but that's not important here. We are just splitting our data. You are splitting your data into your train and test. And please go, that's why I emphasize that we are building on the bootcamp. So go and check. I explain in multiple videos what is train test. And we are dividing our data into 0.3. And now what we are doing here is the neural net. This is the, the Bible. I'm importing my TensorFlow SPF. After importing my TensorFlow, I'm importing a function called sequential. So what is happening in this sequential function? Let's just do this. This is the Bible here, guys. This will tell you everything. And you will be practicing this code. I will give you this code today. We are doing a sequential model. We have here input that you had x1, x2, x3, and together they are going in the neuron. Whether you have your 1 and you have activation function. You have y1 plus y2 plus y3 is equals to y, and you have activation function that converts into 0 and 1, the entire data. And here, guys, you can choose. So now here you have a sequential model because everything is one sequence to another. So this is first step, then second step, then third step. And in the sequential model, you are putting something called embedding, which was your, embedding here. And this embedding, you got it from the top. And here you have, this is all the embedding that you're getting from the top. Now, after the embedding you got from the top, you are flattening the embedding because your embedding, it is a 2D matrix. If you remember from yesterday, your embedding was a 2D matrix, right? Your guys embedding is a 2D matrix and you flatten it to one array. So from 2D, you flat into 1D. And this is your matrix here. So we flat it. And after that, we are applying a activation function. And here we have 16. So what is happening, guys? You can choose your layers. How much do you want? Today is your first code, so a little bit complicated. But these are the codes that are repeated in every project. So here you have a code, den 16. You can choose here. What happens, guys? You can choose, for example, here, you can choose how many neurons you want, right? You can want 16 neurons. You can also want 32 neurons, depending upon what you want. So initial data will be depending upon how many parameters we have, x1, x2, and x3. This goes inside the neurons, right? Sorry. So when you draw it, you have to draw in a way that each of the parameter is going to one neuron. This is very important. So this is one decision maker here. This is another decision maker here, x2, x3. Now this is another decision maker here. And now this is the fourth decision maker here. So now you see it's a voting going on. All these neurons, they take input from each of these inputs. And this will be your Y. Now you can choose either 16 neuron here. You can also do 32, 64. You have a lot of computation, bigger problem, choose 1028. How many neurons you want? That means each of these neurons act as a decision maker. And finally, it is connected to another. Now, decision from all of them will be connected to the next layer. Right? Now, decision from all of them will be connected to the next layer. That is how the neural network is working. And you can choose, that's why here we have chosen 16 here. And at the final stage, you have one neuron, right? That is your output layer. So they have created this entire thing like this, right? You have your embedding that you flatten it. Then it becomes x1, x2, x3. It goes inside these neurons. And then we apply in every neuron, we are applying an activation function, which is your ReLU or sigmoid. What it is doing? Converting your initial data to 0 and 1. Right? So intuitively, guys, you should, ask ChatGPT, ask whomsoever to explain this 5 lines very well to you. And if you understand these 5 lines, you actually did a lot. This is the Bible here, right? Now, in the next thing, in the next slide, so this is okay. we understood how we are building this model. In the next lecture, I will talk about optimizer, losses, and accuracy. So now, after I have built the model, I am trying to compile the model. That means I am just trying to tell, please use this optimizer, which I will talk about next time. Please use this loss entropy function. I will talk about next time. And then also I want accuracy, because I want certain accuracy. And then we have here model.fit. Simply fit my model into train. That means, as I told you, X train is getting fitted to Y train, and do it 10 times, uh, and do it in the batch size of 2. That means batch size is, if I want today to you to learn the entire boot camp, what will you do? You will say, Shraddha, I will only learn 2 chapters at once, or I will learn only 3 chapters at once. That is your batch size. And then you are evaluating loss and accuracy. And I will come to this part in the next slide because it needs a little bit theory development. But if today, with 1 hour of lecture, you are able to understand how this thing is working, this lecture was very, very successful. Otherwise, guys, it takes a lot of times on internet to understand like what is going on intuitively, right? So overall, today's focus will be, and I will give you the code just after this thing, share this code to understand this thing, how you create a neural net. And in the next one, I'll talk about this. And then if you train it, now on screen here, this, because I trained this model, this is a new message. You won a free car, meeting tomorrow. Now it is predicting, this is a new message, and it is predicting that it's a ham, you won a free car. It is also doing a wrong prediction. Even this is a, this is, this is a ham here. This is doing a wrong prediction here. It's a spam. Because my accuracy, I only trained it for 10 epochs. My accuracy is only 0.33. Also, my data set is very small. But this is just a toy problem. So today, go home and please try to understand how this is built. And I will give you the code and play with it. Sounds good to everyone? Do we have questions? I'm close to finishing this. Guys, these 3 classes are very important for you. Then it becomes very easy. Boot camp after Christmas holidays become very easy. It becomes extremely easy. Because there are concepts that you have already understood, right? So now I will provide you with the code, and please connect with me with the teams that I have formed, and see you tomorrow. Bye-bye. See you next time. Bye-bye.
Thanks. Bye.
Bye.
Bye. Bye.
Bye.
Goodbye.
Bye.